Hello, buddy. Welcome. So today we're gonna do problem 4 right now in this video. Problem 4. Um, so let G be a group, and we're going to define H to equal to all elements of the group G that have the property that they have finite order. That is, they're written as their order is less than infinity. That just means they have finite order. So our problem is to prove, our question is we're wondering whether H is a subgroup of G or not. Right? That's the question. And obviously, whichever one you think it is supposed to give a justification. Alright, let me erase that. So the goal is to give a justification, whichever one you decide it is. Whether it's if you think it's a subgroup, you give a justification. If you think it's not, you gotta justify as well, right? And this is a problem that we need to solve. I hope it's very clear, right? So we have a group G. H is like a set, and it's a set that takes things from G, elements of G, and in particular it only takes elements of G that have finite order, right? Order less than infinity, right? And we want to know whether it's a group or not, right? And that's our goal. So as usual, I'd advise you to try and solve this problem on your own first, right? And only when you're completely stuck and have no way to continue, come back over here and we could work on it together and see how this works out, right? So solution. Let's dig in. Let's do the dance, right? So firstly, we do not know whether H is a subgroup of G or not. We are not sure. So what natural thing to do is to play around a bit, right? Well, suppose let's take G and small h. Let's suppose those are elements of H. Well, if they're elements of H, then it means they have finite order, right? That's what it means to be an element of H. It means you have finite order. So that means that then there exists some n and m, right? Positive integers n and m, such that, for example, G to the n equals to the identity, and H to the m equals to the identity, say, right? And so that's what it would mean for elements G and H to be members of the set H. They have finite order. Well, now, if H were to be a subgroup of G, right? If H were to be a subgroup of G, one thing for sure is that a subgroup is first of all a group, right? It's smaller than G, but it's at least a group. So we'd expect one thing to hold, that closure must hold, right? So H must be closed, right? If H is not closed, well, then we might as well forget about H being a subgroup of G, because it's not even a group to begin with, right? So to prove that H is closed, or to think about the closure of H, we'd have to show that for G and H, for example, we need GH to be an element of H as well, right? Well, that would mean that we should be able to raise GH to some positive integer and have our result equal to 1. So naturally we make a guess. What if we raise GH, looking that G to the n equals to 1 and H to the m equals to 1, we might make the guess, how about GH raised to the power nm? What does that give me? Well, that gives me GH times GH times GH, of GH is being expanded nm times, right? So we have nmg's over here, and how many h's do we have? nmh's. Well, now notice, if somehow a miracle could happen and the elements, the h's and g's actually commute, then we could pull the g's to one side. So we'd have g times g, blah blah blah. All the g's would move to the left, nm of them, and all the h's would move to the right, nm of them. And so we'd have g to the nm times h to the nm. And this fantasy of ours would lead us to conclude that since we know that g to the n is 1, g to the nm will be the same as saying 1 to the m, otherwise known as 1, right? This part just 1. H, we know that h to the m is 1, so h to the nm would be kind of like 1 to the n, which is also 1. And so here what what would have is that gh has actually been raised, g times h has actually been raised to a positive integer, giving us a result of 1. And this would kind of mean that gh is an element of h, as we're trying to check here, closure, right? But notice we had to do some wishful thinking here, and our wishful thinking happened when we assumed that you could pull the g's on one side and you could pull the h's on one side. That is, we kind of assumed here that g and h, the g's and h's commute, right? And this is where now we get our intuition that maybe it's not the case that h is a subgroup of g, because we know for sure that not all groups commute, right? Not all groups commute. You're not necessarily allowed to do this, right? And this prompts our question. Maybe it's actually not true that h is a subgroup of g. And thinking of that, we're like, what groups do we know? What groups do we know that don't commute, right? Or doesn't commute? Or what group do we know that is not abelian, right? That becomes the question. Well, in the previous video we saw a favorite friend of ours known as GLNC. It's a group that does not commute, right? In particular, we're going to think small. Let's go GL2C. Why? Because it's the smallest set of matrices we know of, right? Otherwise you're going to have GL1, which is just an element, but GL2 is the smallest reasonable matrix that we have, and it's easy to work with. So this prompts us to maybe take GL2C and see if we can produce a counterexample. Well, what would producing a counterexample entail? Well, it will consist of getting elements, an element of GL2C. We're going to get another matrix B element of GL2C. Now we're going to have that A actually has finite order, let's say n. A to the n actually equals to 1. And B has finite order, say B to the m equals to 1. Well, that would mean that A and B, right, are actually elements of H, right? But now to make it a counterexample, to make it falsify the statement, we'd really want to have the following happen. We'd want to have that although A and B are elements of H, AB is actually not an element of H. That is, we want it to be true that you can't actually raise AB to some integer power and get 1. That can't happen, right? If we do that, then you agree with me, we're done. We'll have proved that AB has a no order, infinite order, right? That no order is the same as saying infinite order. Well, that would then mean that if we get two elements that are in H, multiply them and get some that's not in H, that would mean that H is not closed. And if H is not closed, it's not a group. If it's not a group, how the heck can it be a subgroup, right? Because a subgroup is at least a group, right? So then our task seems to be finding these A and B that satisfy all of these cool properties. Well, you're just in luck, because we do have such examples, right? So set A equals to, say, 0, 0, 1, 1. Notice something. What's A squared? A squared is 0, 1, 1, 0 times 0, 1, 1, 0. When you multiply out, this gives us the identity, right? Remember, we're dealing with GL2C here, so the identity is actually a matrix, right? The identity matrix. Well, notice something. If A squared gives me the identity, it means that A has finite order, right? A has finite order, right? Well, if it has finite order, then it means that A is actually an element of H, right? So we're doing okay so far, because we're trying to find a counterexample. Remember, we want A and B to be elements of H. Well, now let's find a B. Well, what if we set B equals to, I don't know, C 0, 0, let's make this 3 and let's make this a third. Well, what's B squared gonna be? b squared is going to be 0, 3, a third 0 times 0, 3, a third 0. Well, when we actually do the multiplication, we end up with 1 over here, 0 right there, 0 right there, right? And then we end up with 1. Miraculously, once again, we see that b has finite order. Finite order. Well, if b has finite order, well, then it means that b is actually an element of H. So we've succeeded in finding a and b that actually belong to H. So now we have a and b elements of H. Well, to finish creating a counter example, all we need to show is that a times b does not belong to H, right? So let's actually do that. Well, a times b, if you recall what our values of a were, a was 0, 1, 1, 0, and I think b was 0, 0, 3, 1/3. I hope I haven't forgotten this. So let's see. Especially b. A was 0, 1, 1, 0. Yeah, and b was 0, 3, 1/3, 0. So that's accurate, right? So this is what we have. 0, 3, 1/3, 0. Well, when we do the multiplication, right? Pen's jamming. It always jams. The question is, when is it gonna jam, right? So when we do the multiplication, we end up with a third. A third over here, right? We end up with 0 over here. We end up with 0 over there. And we end up with 3 over here. Right? We have 3. Alright, so now we just need to prove that this thing actually is not an element of H. And to do that, we'd have to show that it has infinite order. That is, you can never raise this matrix, otherwise known as AB, to some power m, right, to some positive integer, and have it equal to 1. Well, notice, let's actually do some calculations here. Well, a third, alright, so I'm moving slowly here because, right, this matrix squared equals to a third squared, right? Alright, a third squared, 0, 0, and we have 3 squared. Alright? Curious. Well, did we just run out of space? My handwriting is big too. Well, anyways, alright. So now we have a third again, right? What if we were to cube this? What if we were to get a third 0, 0 and cube it? Well, this matrix cubed actually, right? Let me write it out. Oh wait, I think my pen is back in action, so that's good. When we cube this, we end up with, well, a third cubed, 0, 0, 3 cubed, right? Let me put it like this so you don't get confused, right? Well, this kind of suggests, and you can check on your own, but if you get any positive integer, right, and raise this matrix to the power n, right? Remember, this matrix is AB. AB raised to the power n for any positive integer is gonna give you, as you guessed, 1/3 to the n times 0. This is 0, 0. This is 3 to the n, right? Well, notice something. There is no way this 3 to the n is actually gonna give us 1, right? This n, for positive n, this will never become 1. At n equals to 1, it's 3. At n equals to 2, it's 3 squared. N equals to 3, it's 3 cubed. It only grows bigger and bigger. There's no way it's ever gonna equal to 1, right? And the same thing here. It gets smaller and smaller, but certainly doesn't get closer to 1. It's 1 over 9, right? And so what I'm trying to say here is that AB to the n can never be equal to this matrix, the identity matrix. Well, if there is no integer, if there is no positive integer to which you can raise a times b to get the identity matrix, then it means that a times b does not have finite order. that the order of A times B is infinite, right? The order of A times B is infinite. Well, that's good, because that means that, as we're trying to say, A times B is not an element of H, right? But now you see we have a problem, because A has finite order. We saw it has order 2. A squared gives you the identity. B has finite order. B squared gives you the identity. So A is an element of H, B is an element of H. But A times B has infinite order, is not an element of H. Well, that's another way of saying that A and B, that's another way of saying that H is not closed. But if H is not closed, it means H is not a group. Well, if H is not a group, then it's certainly not a subgroup, because a subgroup is, at the very least, a group. So we've actually presented an example that shows that an example where H is not a subgroup of G, and which means that in general H is not a subgroup of G, right? However, you might not be very satisfied with this proof, and I understand completely why. Because you ask yourself, sure, the counterexample works, but how the heck was I supposed to know, for example, that think up an example like A and B, and know that A times B is going to be such that A times B has infinite order? Maybe it's easy to guess this one, you might be thinking, but how about this one? This seems to come out of nowhere. 3 and a third, that seems so random, right? So that's what I'm going to do now. Let's try and motivate it. Let's see how you'd be able to guess or come up with something like this. Of course, we can't ignore the intuition element, but it's actually sensible where these things come from, right? And so let's make it clear first, right? Let's trace this trajectory to actually figuring out what those matrices are. So we start the problem a little confused, right? Is H a subgroup of G or is it not? We do not know. So we play around a little, right? We get some elements of H, right? We know that they have finite order, right? And then we want to show that, we want to check if closure even works, because if H is not closed, then it's certainly not a subgroup, right? So we want to check closure. Is GH actually an element of H? And we make this inspired guess, right? GH to the NM, right? Based on the fact that the order of G is N and the order of H is M. We do the multiplication and realize that this only works out. It only gives me 1. GH only has finite order if somehow the G and the H is commute. We can pull the G's on one side and the H's on one side. And this immediately prompts our memory, because we know that not all groups are commutative. So we think, maybe if the group weren't commutative, we might never be able to find some positive integer, and some positive integer that actually we can raise GH to get 1, right? GH might not actually have finite order. And then we think to ourselves, what examples of non-commutative groups do I know? And one glaring example comes to mind, GLNC. And we think to ourselves, well, GLNC is too general, right? We need to have a matrix that we can manipulate to create counterexamples to show that this is actually not true. And well, what's the smallest and simplest matrix you can work with? It's matrix of 2 by 2. So GL2C is a natural example, right? And so our task now remains to find two matrices that have finite order, but that the product of them never has a finite order. It has an infinite order, right? So now the question becomes, well, how do you come up with these matrices, right? How can you logically come up with these matrices? Well, let's see how one might be able to do that. Let me also see if I can have some space. Oh, I actually do have space. All right. So one thing we know is that we're trying to find a matrix, a 2 by 2 matrix that has infinite order. Well, that means that I wanna be able to plug in values, and the more I multiply this 2 by 2 matrix, the farther away this value and this value goes from 1, right? Because for it to have finite order, after multiplying we need to have 1 1 0 0. So we want to make sure that this entry right here are as far away as possible from 0 every time you multiply, like for every power you raise this matrix to. Well, notice that as a natural example is any matrix of the form AB when raised to the n, right? So this is something that's worth knowing. Any matrix of the form A00B raised to the n, where n is a positive integer, is actually of the form an to the 0, 0, b to the n. Well, this is good to know, because if one of these is not 1, then a to the n can never equal to 1, right? And so this is where we get the example of a matrix that has infinite order, an order that's not finite. So now our task becomes find two matrices A times B, which when you multiply them you get this matrix, right? That really becomes our task. Well, and then we realize that anytime you have matrix of this form, anytime you have a matrix of the form 0, 0, AB times a matrix of the form 0, 0, CD, something interesting happens. When you multiply them, you actually get a matrix of this form, right? Because we want a matrix of this form. Oh, sorry, maybe I should have erased the power here. So what we want is a matrix of this form, AB. So that when we raise it to the nth power, it only goes farther and farther away from 1, right? Well, notice if you have two matrices of this form, say A and B, well, multiplying them out gives me in this entry here BC, in this entry just 0, right? In this entry here 0, and in this entry AD. So matrices that have only this diagonal present have this weird property that when you multiply them by each other, you get another 2 by 2 matrix, but where the diagonal that's not 0 is this one on the opposite side to these two, right? That's an important property of the matrices here that's helping us, right? And so our task really becomes now, so we know what type of matrices A and B have to be, but the thing is we need A and B to have finite order. Well, naturally multiplying matrices is kind of hard. Right? We don't want to multiply, like, let's say we don't find something that, let's say, has an order of 6, multiply the same matrix 6 times. So naturally we want to find the smallest order possible, and in this case it has to be 2, right? Because if the order was 1, then we'd have the identity matrix, right? So we want to get a matrix of the form 0, 0, AB, raise it to the power of 2, and end up with the identity matrix, right? That's really our challenge here. Well, any matrix of the form A00B when squared, right, we're just going to square this, is going to give me what's it going to give me actually? AB, right? It's going to give me AB over here. It's going to give me for this entry it will be 0, for this entry it will be 0, and for this entry it will be AB. So it seems then, so long as if I want to make this squared, which is the same as this, equal to 1, 0, 0, 1, it's important that AB equal to 1. So all I really need to do is to find choices of A and B such that AB equals to 1, right? And so now it makes perfect sense, because if we set A equals to 1 and B equals to 1, then AB certainly equals to 1. And so for our choice of matrix A can be 0, 0, 1, 1, right? Which is what we actually chose for our matrix A to create a counterexample. And our choice of matrix B is going to be again something such that the product, right, the product of the diagonal DC actually equals to 1, right? Because then it will have finite order, an order of 2. Well, we could try 1. We can't try 1, 1 again because it just gives us 1. So anything works. In our case, we tried 3 and a third, because 3 times 1/3 actually equals to 1, right? And so AB suddenly gave us what we're looking for, a counterexample. Now, of course, notice what this suggests. We chose, for sure, we chose A equals to, we chose this value of A equals to 0, 1, 1, 0, and B equals to 0, 3, 1/3. But really all we needed was these off diagonal to have the property that the product equals to 1. So in reality we could have chosen any A, any A that's of the form any A that's of the form 0 0, sorry, it's the other way around. So okay, let me erase this. Hope my eraser works. Alright, so what we're really saying is that any A that's of the form 0 0 where this product equals to 1, for example n1 over n, right? Here the n's are just complex numbers, obviously, right? So, and another one B, which was of the form, for a different n, we don't want the same n here, let's say m 1 over m. Well, any matrices of this form would have had the property that when you square it, you get the identity matrix. When you square b squared, you get the identity matrix. And AB has infinite order. So we have infinitely many counterexamples, right? And so that explains where we got 1/3 and 3 from. We just set m equals to 3 for B, so we got 3 and 1/3, and we set to get A equals to 0 0 1 1 0, we just set n equals to 1, right? Okay, so that's kind of one possible path of coming to this, but there are many ways to arrive at it, right? So yes, we are done with our proof, and we need to, one can think of what kind of things helped us to solve this problem. Well, in particular, realizing that the subgroup of a group is a group, and so for starters, it must be closed. This is important, right? And because all our proof hinged on proving that it's not closed, right? The other thing we noticed, as I had mentioned in the previous video, is that GL2C is a very nice group because it's an example of a non-abelian group, and we used it here to create a counterexample. The other thing that we notice is that studying matrices is actually pretty valuable, right? Because, for example, what we know is that any matrix, so you have 0 0 AB over here, when raised to the n, just raises things to the n. So when you're trying to think of an example, when we're trying to think of an example of a matrix that has infinite order, a natural example should be a matrix of this form, where A and B are not both 1. One of them could be 1, but the other one has to be something else, right? And of course, other really fun properties we just learned from this whole thing, right? I know it was long. Right? Another thing we learned is that if you have a matrix where these diagonal entries, these entries are not 0 and these ones are 0, and you multiply by another one where these entries are 0 but these ones are not 0, always gives you something of this form, where these entries are the non-zero ones and these are the 0 ones, right? It actually turns out that the reverse actually also works, that any matrix of this form too, I think, but please verify, right? I might be kidding you here. These are the non-zero entries, these are 0, these are 0, also gives you something of the desired form, right? And this form is really nice for us because if these entries are not both 1, you raise it to the n and suddenly you can never get the identity. It's a good example of a matrix with infinite order, or an element with infinite order. Alright, thanks for sticking by, and I hope to see you on the next video. Bye.